What is shear? I want you to imagine a beam, and I've drawn the center axis of that beam. I'm going to talk about the types of load that we could put on that beam. If I were to grab one end of the beam and pull away, then I would be putting that beam under tension. But by contrast, if I were to grab that beam and push inwards, put an axial load into the beam, then I would be putting that beam under a compression load. Another kind of load is, I want you to imagine this vector is pointed outwards at your face, and it would cause one end of the beam to rotate around its center axis, and so that's a twisting or a torsion load. But the kind of load that you'll be studying are loads that are perpendicular to the center axis of the beam, pointed up or pointed down. Either way, we call these shear loads. Now, I want to say that if we put a beam under a shear load, as you will be doing, this is a statics problem. The beam will bend and then maintain a static position. It's not in motion. And to maintain equilibrium, there has to be an equal and opposite force. And that equal and opposite force is going to come from the pivots, or the two fixtures on either side of the beam. All of the forces have to sum to 0. Another thing that I'll say is that we're going to work on modeling V as a function of X, or a horizontal position in the beam. And here's an example. Imagine a beam with two simple supports on either end, or pivots, and this beam will be 10 meters long. Further, imagine a evenly distributed load in the center of the beam, like a pile of sand. And so we have 3 newtons per meter distributed over the center 4 meters of this beam. Now that puts a total load of 12 newtons on this beam, and this is a statics problem. So what that means is there has to be an upward force of 6 newtons coming from each of the 2 pivots. And so I want to know what V of X is. A couple of notes. X is between 0 and 10, right? That's the domain. The units for X are going to be meters, and the units for shear are going to be in newtons. It's a force. Now V of X is defined to be the sum of all forces perpendicular to the beam's axis to the left of X. What that means is, if X equals 2, I'm only looking at forces to the left. I'm only looking at this single force. If X equals 8, I need to look at all of these forces as well as this point force over here. Also, we have a convention. We have to talk about positive and negative shear. A downward pointed force to the left of X will correspond to negative shear, and an upward pointing force will correspond to a positive shear. Okay, so now, if X is anything between 0 and 3, there will be only a single force to the left of X, and it is 6 newtons pointed upwards. And so what that means is V of X will be constant at 6 newtons all the way from X equals 0 to X equals 3. By contrast, if X is anywhere between 7 and 10, we have to look at 2 different forces. There's a point force over here of 6 newtons pointed upwards, and there's a total of 12 newtons from this pile of sand pointing downwards. And so V of X is constant on this interval again, from X equals 7 to X equals 10. And V of X will be 6 minus 12, negative 6 newtons. In the center, between 3 and 7, we've got the single upward force of 6 newtons, and this downward force, this evenly distributed downward force, will be linearly growing from 0 to 12 as X grows from 3 to 7. And how can I model this? Well, here's a graph. X equals 0 to X equals 10. I have shear here on the vertical axis. And so I said that V of X was constant at 6 newtons from X equals 0 to X equals 3. And there's a downward force linearly growing from 0 to 12. In other words, V is linearly changing from positive 6 to negative 6 as X proceeds from 3 to 7. And so I can indicate that with a downward sloped line. And we agreed that v of x would be constant from x equals 7 to x equals 10. And so I have another horizontal line on the right. And so now I've used my load diagram to create a shear diagram.